Welcome to Linked Data Engineering, lecture number 3, Linked Data Vocabularies and Ontologies. This is part 5 of the lecture, OWL and Beyond. And in this part of the lecture, we want to continue our discovery of OWL, and we want to talk about OWL properties and restricted properties that are an interesting complement to the complex classes that we have already talked about last time. And in the end, we want to ask the question, is it sufficient with OWL? Can we really represent all the knowledge that we want to represent with the help of OWL? Or is there something which is beyond the capabilities of this language of knowledge representation? Okay. We are still here in the modeling layer of the semantic web, and of course, we are talking about OWL, the web ontology language. Property relationships. So how can properties somehow be related with each other? The first one we know already, there are property hierarchies already in RDFS. It means that a property can be a specialization, for example, or also a generalization of another property. And you do this with this RDFS keyword, RDFS sub-property of. You see here also the first example we have is made of as an OWL property, and we define it to be a sub-property of consist of, which is logically okay. The second one would be an inverse property. So one property means exactly the opposite of the other property. If this is the case, then you define this property to be OWL inversive of another property. So OWL inversive of here is a property. Look at the second example, reads. It's an object property, and we say this is the inverse of is read by, which means, for example, a person reads a book, then the inverse of means a book is read by some person. And the point is, if you declare a property to be the inverse of another property, it means if then a person A reads a book B, then with the other property, it holds that book B is read by person A. Then there is the possibility to declare two properties to be identical, and then you say this is an equivalent property. You have here the OWL keyword, OWL equivalent property. This is the last example. Composed of, for example, is here an object property, and you can declare this to be equivalent to consists of. Okay, but there are more possibilities how properties can relate, or what kind of properties themselves can have. Think of transitivity. Transitivity is quite easy. It means if A is related to B and B is related to C, then if this property is transitive, A should also be related to C. This is a transitive property, so you have an example. If A is part of B and B is part of C, then it holds that A is part of C. And you can declare a property to be transitive with the help of this OWL transitive property class. And if you declare a property to be member of that class, then this condition will hold. Next thing, you can declare two properties, or one property can have the property that is symmetric. What does that mean? It means that if two individuals, A and B, are connected via that property, then it holds also in the opposite direction, that B via the same property is connected to A. Then it is symmetric. Simple example here is the property is neighbor of, so A is neighbor of B, therefore it holds that B must also neighbor of A. Then there are some properties which are functional. What does that mean? Like in a function in mathematics, you know that, for example, it means that an individual, if a property is applied to that, can only have one function value, one other individual it is connected to. A simple example is, for example, has mother, and then if you have these two property instantiation, A has mother B and A has mother C, therefore, if the property has mother is declared to be functional, it holds that B must be equal to C. So this means functionality. In that sense, one individual can only be mapped to one other individual and not, again, to another one. And then, of course, there is also the reverse of this functional property, which is then an inverse functional property, and there it's vice versa. Just think of the inverse of has mother would then be is mother of, and then the same condition, the functionality condition, then here holds, for example, for the first argument. This means if B is mother of A and C is mother of A, it must hold, if this property is declared to be inverse functional, that B must be equal to C, so it must be the same mother. So functional and inverse functional means the same, once for the first argument and the other for the second argument. Okay, these are property relationships. Let's look at an example how, for example, a transitive property can be declared. Here we have the property is published before, and this is an object property. And we declare this object property to be a transitive property. Then we say, okay, domain and range here is the same, it's book. That's also quite handy because if it's transitive, it should be applied again and again. Which means here, for example, we have the instantiation Animal Farm, which is a book, is published before 1984. And Brave New World also is a book, is published before Animal Farm. If I declare then is published before to be transitive, then it can be inferenced via a reasoner, for example, that Brave New World has been published also before 1984. So this is then implicit knowledge which can be deduced from the fact that this property has been declared a transitive property. Let's look at more property relationships. We have seen symmetric properties, therefore also asymmetric properties exist. What's an asymmetric property? It means then if it holds that A is related to B, then it's not possible via the same property that B is related to A. Simple example is left of O. If A is left of B, then it's not possible that B is also left of A. This would be an asymmetric property. So in some situations this is quite interesting and quite useful. Properties also can be reflexive. What does that mean? For a reflexive property, it always holds that each individual upon which this is applied, there definitely must hold the relation that this individual is related to itself via exactly that property that we are using to. So, for example, if you have x and the relation is related to, then x always must be somehow related to itself. So x must be related to x. Reflexive means the thing is always related to itself. If something is reflexive, then you also have the possibility to declare things to be irreflexive, and there exactly the opposite holds. So it means that via a property which is declared irreflexive, an individual can never be or must never be part or related to itself. Example of that is, for example, if x is parent of y, then x usually should not be equal to y. So then x is different from y. So is parent of is a relation where an individual is not related to itself but to some other individual. And therefore, this is irreflexive. What else can we do with properties? We have learned about disjunctive classes, therefore also disjunctive properties are possible. For classes, it was clear that if a member cannot be in the same time member of two classes, so it's either in one class or in the other, but never in both, this means disjunctive. And this is the same here for properties. So consider two properties R and S, and they are disjunctive if two individuals x and y are never related via both properties. So two individuals x and y are either related via R or via S, never via both. Then these properties are disjunctive. Now you might wonder, is this somehow useful? Yes, it is. For example, here we have an example. We declare has parent, and we say has parent should be disjoint with has child, which means if A has parent B, then A does not have child B. So then the relation between A and B has child does not hold. So you see there are in reality, of course, disjunctive properties, disjunctive relationships, and therefore we must have a way to express them, and OWL offers you a way to do that. And again, in the same way, like for classes, we had a shortcut to declare several classes at the same time to be disjunctive. We can do this with properties, and it's exactly the same way how it works. Only, of course, the class here has a different name. You define something to be of type all disjoint properties instead of all disjoint classes. And then you say this is a construct, and you say the member of this construct are here given in parentheses, and you have then a collection of the properties which have to be declared to be disjunctive among each other. So you save a lot of definitions via that shortcut. One last thing to say to properties is if there is a relation between A and B, I must also be able to express that a specific relation might not be between two individuals A and B. And this would be a so-called negated property instantiation. For example, if I want to say that two persons are not related, for example, by family, that A is not brother of B. If I have the relation as brother, and then I want to say A is not brother of B. How do I do that? In OWL, you do this with a so-called negative property assertion. And this works, if you look at the construct here, about the same way like you have in mind or that you remember already from RDF, which was the RDF reification. So here you declare a new construct, which is an OWL negative property assertion. And then you say, okay, what is the source individual? Here in our example, for example, it's George Orwell. And what is the target individual? In our example, it's Aldous Huxley. And then you say the assertion property on which you pose this negative property assertion is brother, which means George Orwell is not the brother of Aldous Huxley. And this is a negated property instantiation. So you are able also to express the two individuals are not related with each other via a specific property. Okay, the last point about properties that I want to show you is the so-called property chaining. Therefore, you are able in OWL to construct complex roles in a way like you know that for classes, which means complex classes can be constructed out of more simple classes, and in the same way complex roles can be constructed from simple roles. And then you end up in something in your knowledge base where you have the T-box, you remember that, terminological knowledge, and A-box, assertional knowledge. There is a new box which is called R-box. Often this is also part of the T-box. R-box is then the role box, and their complex roles or complex properties usually are declared. Okay, let's look at the following example. The friends of my friends are also my friends. This is a complex property, but of course, this can be rather easily constructed by declaring has friend is a transitive property. Then if A is friend of B and B is friend of C, it also holds that A is friend of C. This would be transitivity. But now just think what happens if this chain would be subject to a change of properties. For example, in the following example, the foes of my friends are also my foes. So A is A is friend of B, and B has the foe C. Then this would mean that C is also the foe of A. How do I declare something that my friend's foe? Yeah, so this cannot be usually expressed in the way we know already. So this would mean A has friend and B has foe C, and therefore A also has foe C. Complicated thing. With first-order logic, of course, this would be possible, but first-order logic is more complex than OWL, so this is something which is not possible in OWL. There, you, for example, can use a fully fledged quantifier here. So, for example, you use here a universal quantifier and say for all x, y, z, it holds that, and then you define a rule, an implication here, that if x has friend y and y has foe z, then it holds that x has friend's foe z. This would be a quite easy definition. How can this be achieved in OWL? With the help of a so-called property chain axiom. There you define also a role which is called has friend's foe, and you say this is an object property, and this object property will be defined in the form of a property chain. So it means you define here simply, you say has friend's foe, has the OWL property chain axiom, and then you write in parentheses the properties from which this property is constituted. And first you have has friend, and then you have has foe. And therefore, exactly you map to something which is shown here below on the right side. So A has friend B, B has foe C, therefore A has friends for faux C. So this closes then here the chain and the cycle. Property chains in OWL are a complex matter. Therefore, if you really want to apply them, there are certain restrictions that hold. We won't go into detail about these restrictions. Please keep in mind that if you are using property chaining, then you have to be careful because there are a few rules to keep all the necessary computations in a way that it's still decidable. Therefore, often it is not used to avoid the problem that you run into undecidability. What does undecidability mean? For example, that a reasoner that is based on, for example, some basic problems like to find a satisfying condition to fulfill a formula won't come to an end because it runs forever by looking for something like that. So this means undecidability, if the algorithm for this decision process won't end. And if a logic is too complex from its expressivity, then it simply runs into undecidability. Therefore, OWL, special care has been taken of, especially for that case, is formulated in a way that they try also to be decidable. And not only that, there you have seen in the beginning, there were also some minor flavors, subsets of OWL, which are not only decidable, but which are also of lower complexity, of polynomial complexity. Okay, so this is property chaining. In the end, before we close this chapter, I have an addendum or two addendums for class definitions. One is the so-called qualified number restriction. You might remember that we can define classes with the help of number restrictions. For example, we could define a class that there are only instances in the class which have a special, let's say, property connected to them, and this must occur at a specific number. Let's say 4 times for a string quartet. A string quartet is something which has exactly 4 members. So each individual which is of class string quartet must have 4 members. So it must have the relation member, and then you have this once, twice, thrice, and for the 4th time. So this is a number restriction. And of course, you can also not say exactly, you can also say less than or greater than. And this, of course, can also be here used with the help then that you not only say you have to have exactly 4 members, you also can restrict the class membership of these members and say a string quartet exists of exactly 4 members who are violin players, then you would have something like that, a qualified number restriction. Let's have a look at our example here that we are given here. Just have first a look at the description logic example, which is the gray one above the box. We define here something which is a successful author, and we say a successful author is somebody who has as notable work at least 1 bestseller. Makes sense. How do we rephrase this in OWL? We say successful author is an OWL class, and this is a subclass of a more complex compound, which is a restriction on the property notable work. And then we have the new keyword OWL min qualified cardinality 1, which means exactly, okay, qualified cardinality, this is not only a cardinality which reflects on a restriction on the property, but also restricts the class and specifies a specific class. This means qualified. So therefore, we must then add another line which says on class bestseller in that case. Quite easy. And then, for example, min qualified cardinality means at least 1 here. Then you could use max cardinality, which would mean at most 1, or you can say exactly 1 with qualified cardinality. Very last addendum for the classes. There is a so-called reflexive property restriction. You can define classes with a reflexive property restriction, which means you define classes which have a property where all individuals of this class are connected to themselves. So this property must be somehow reflexive. And you do this with the following construct. We have the example here, which says a philosopher is somebody who knows himself. And then this means philosopher is a class, and this is a subclass of a compound, which is a restriction, and the restriction is on the property knows. And we say, okay, in this property knows, we have a new property which says has self, and this is true. True in the sense that we define here true as a string and we type it as to be of type Boolean. So has self is true means that each individual is related to itself. Of course, it might also be related to other individuals, but it must be related to itself. Otherwise, it would not be exactly in that class. So a philosopher is somebody who knows exactly himself. This would be a reflexive property restriction. So far, so good. So how is the world now that we can define with the help of our old constructs? Is there something out there, or can we say nearly anything? Can we represent any knowledge? Yeah, you have to think of it. The point first is the more expressivity that you allow, the more complex all the processes, all the algorithms will be in the end. And this might lead, as we have already heard of, to undecidability, as it is the case for first-order logic. So do we really need more expressivity than OWL, OWL-DL, OWL description logic, this is the language we have just talked about, offers? I have an example for you. How would we define a squanderer? How would we represent it in OWL? A squanderer is a person whose expenses are higher than his income. This is quite difficult because there are only individuals in that class for which their specific expenses are higher than their specific income. No idea how to rephrase that in OWL. So we could say, okay, a squanderer is a person. We could say a squanderer has some expenses. And we could also say that a squanderer has some income. But this more or less is it. So we need a constructor that is able here to combine first-hand classes, second-hand somehow properties. So a tool, something that mixes T-box and A-box. This is in OWL not really possible because here A-box, we have to take care in the class description of a specific value of an individual. This is the expenses and the income of this individual. And this has to be transferred into the T-box. So this is in OWL not possible. It could work in, for example, first-order logic. And this is a nice example where you see that first-order logic really is more expressive than OWL. Here, for example, you could rephrase a rule. Rule is always an implication, as you see here. The first part of the rule is connected via conjunctive facts or conditions that you say here. And then in the end, you have done some outcome of the rule. So the head of the rule means, okay, this is the outcome of the rule. And then you see here, for example, we would define a rule in the following sense. For all x, y, and z, it holds the following fact. If x is a person, and if x has income y, and x has the expenses z, and z, which are the expenses, are greater than y, which is the income, then x is a squanderer. Now you might say, wait, this is an arithmetic operation, z greater than y. This is not part of first-order logic. No big deal, I would say. Then we define a new property or predicate in first-order logic, which has the name greater than, is applied on z and y, and this should reflect exactly the arithmetic operation z is greater than y. So greater than is true if z is greater than y. Then you can do this in first-order logic. The problem then is first-order logic is undecidable, therefore this would not be what we want. We want to have decidable or even faster algorithms. So therefore, this is not allowed in OWL. You see, there is something beyond OWL, but OWL will be sufficient for our case. And in the next part of the lecture, we will talk about RDF and RDFS knowledge bases as well as OWL knowledge bases.